friends, I am Akshat from the Centaurs team. We are mostly surrounded by solids and we use them more often than liquids and gases. For different applications, we need solids with widely different properties. These properties depend upon the nature of constituent particles and the binding forces operating between them. Therefore, study of the structure of solids is important. The correlation between structure and properties helps in discovering new solid materials with desired properties like high temperature superconductors, magnetic materials, biodegradable polymers for packaging, biocompliant solids for surgical implants, etc. From our early studies, we know that liquids and gases are fluids because of their ability to flow. The fluidity in both of these states is due to the fact that the molecules are free to move about. On the contrary, the constituent particles in solids have fixed positions and can only oscillate about their mean positions. This explains the rigidity in solids. In crystalline solids, the constituent particles are arranged in regular patterns. In this video, our team will discuss different possible arrangement of particles resulting in several types of structures. The correlation between the nature of interaction with the constituent particles and several properties of solids will also be explained. How these properties get modified due to the structural imperfections or by the presence of impurities in minute amounts would also be discussed. Enjoy the video.
Crystalline solids has a long-range order. They melt at a sharp temperature. Crystalline solids can be cleaved along definite planes. Crystalline solids in general are anisotropic. It means that their properties such as electrical conductivity, refractive index, thermal expansion, etc. will be in different directions. Crystalline solids are more rigid. Examples of crystalline solids include copper, potassium, nitrate, benzoic acid, etc. Solids have definite mass, volume, and shape due to the fixed positions of their constituent particles. Amorphous and crystalline are two types of solids. Amorphous and crystalline solids differ in the properties such as cleavage property, melting point, shape, anisotropy, etc. Amorphous solids are those solids which has a short range order. Amorphous solids do not have a sharp melting point. They have softened in a range of set temperature. Amorphous solids undergo irregular or conchoidal breakage. Amorphous solids are isotropic. Their properties will be independent of the direction in which they are measured. Amorphous solids are less rigid. Examples of amorphous solids are fiberglass, cellophane, Teflon, polyurethane, etc.
Face-centered cubic or FCC refers to a crystal structure consisting of an atom at each cube corner and an atom in the center of each cube face. It is a closed packed plane in which on each face of the cube atoms are assumed to touch along face diagonals. Each spheres touch one another across a face diagonal. The cube edge length of A and atomic radius R is related through a formula A equal to 2 into R into root 2. For a FCC crystal structure, each corner atom is shared among 8 unit cells, whereas a face center atom belongs to only 2. Therefore, 1/8 of each of the 8 corner atoms and 1/2 of each of the 6 face atoms may be assigned to a given unit cell. So the total number of atoms in each unit cell is equal to 2. The coordination number of the face center cubic is 12 and the packing factor is 0.74. The examples of face center unit cell include aluminium, copper, nickel, gamma iron, gold, and silver. Body-centered cubic is a cubic unit cell with atoms located at all 8 corners and a single atom at a cube center. Center and corner atoms touch each other along cube diagonals, and unit length A and atomic radius R is related through a formula A equal to 4 into R divided by root 3. The examples of body-centered cubic crystal structure include iron, chromium, tungsten, and niobium. Two atoms are associated with each BCC unit cell. The equivalent of one atom from 8 corners, each of which is shared among 8 unit cells, and the single center atom, which is wholly contained within its cell. Therefore, the total number of atoms per unit cell is equal to 2. The coordination number of the BCC is 8 and the atomic packing factor is 0.68.
A body-centered cubic unit cell has atom at each corner of a cube and atom at center of the cube. Its coordination number is 8. In total, it has 2 atoms, one at the center and another at the corner, which has 1/8 of total atoms in it. The total packing efficiency of BCC is 0.68. In crystallography, orthographic crystal system is one of the 7 crystal systems. Orthographic lattices result from stretching a cube from 2 different orthogonal sides with the two different factors, resulting in a rectangular prism with a rectangular base. I am going to talk about body-centered orthorhombic and primitive trigonal. The orthorhombic lattice is a cubic lattice that has been stretched or compressed so that the lattice constants in the 3 basic directions are all different. Its lattice constants are A, B, and C, and all angles are right angles. In this, A is equal to 1, B is equal to 1, and C is equal to 2. In crystallography, the tetragonal crystal system is one of the 7 crystal systems. Tetragonal crystal lattices result from stretching a cubic lattice along one of its lattice vectors, so that the cube becomes a rectangular prism with a square base A by A and height C.
Hello everyone, I am Sudeep and I am going to explain the face-centered cubic. The face-centered cubic is an arrangement of atoms in crystals in which the atomic centers are disposed in space in such a way that one atom is located at each of the corners of the cube and one at the center of each face. This structure also contains the same particles in the centers of the 6 faces of the unit cell for a total of 14 identical lattice points. The face-centered cubic unit cell is the simplest repeating unit in a cubic closed packing structure. So in a nutshell, I am going to sum up. It contains 4 atoms, fills 74% of the total volume. Corner atoms touch the atoms in the centers of the adjacent faces along the face diagonal of the cube. Coordination number is 12. So thank you.
In crystallography, the hexagonal crystal family is one of the 6 crystal families. In the hexagonal family, the crystal is conventionally described by a right rhombic prism unit cell with 2 equal axes A and B, an included angle of 120 degree denoted by gamma, and a height C perpendicular to the 2 base axes.
My name is Lokesh and I am from Centros team in VIT University. Now I'm going to teach you about packing fraction. So first of all, what is a packing fraction? So packing fraction is the amount of space occupied by an atom in a unit cell. So there is a formula for calculating packing fraction. it is the number of atoms multiplied by the volume of sphere. Here sphere represents the atom, so volume of atom divided by volume of unit cell, which is typically a square. So basically there are three types of unit cells. The first one is simple cubic unit cell. It is also known as SCC. And the second one is face-centered unit cell. FCC or CCP. And the third one is body-centered unit cell. ACC. So let's go to SCC. So in SCC, there are 8 atoms occupying each corner of each unit cell, like this. But they contribute only 1/8 of the portions to the unit cell. So there are only 8 into 1/8, that is 1 atom in this unit cell. So while calculating the packing fraction, it is actually I forgot to mention one thing here. We have to multiply this with 100 in order to find the percentage of it. So packing fraction here is number of atoms is 1 into 4 by 3 pi r cube, which is the volume of sphere, divided by a cube. Here the atoms are present in such a manner that they are adjacent to each other, like this. Now let's move on to FCC. In FCC, each atoms are present in corners, 8 corners, as well as on each face of the unit cell. The shaded part represents the atom which is behind the face. That is the face that is behind this face. So the atom in each phase contributes only half of it to a unit cell. So typically it is 8 into 1/8, which is the atoms at the corner, plus half into 6, which is 4 atoms in this unit cell. Now let's calculate the packing fraction. It is 4 into 4 by 3 pi r cube divided by a cube, where a is the side of each unit cell. Here we have to find a relationship between the radius and the side of a unit cell. So the atoms here are present in such a manner that in this way. So effectively here this is R, this is 2R and this is R. So we come to know that 4 times the radius of this atom equals that is this hypotenuse length. This is A and this is also A. So by Pythagoras theorem, this comes out to be root 2A. So R is equal to root 2 times A divided by 4. And we have to substitute this in this formula here. It is 4 into 4 by 3 by root 2A.
So you saw the packing fraction of simple cubic and face center, and now we will see the packing fraction of body center. In body center there are 8 corner atoms and there are one bulk atom at the body of the unit cell. The contribution of the corner atoms to the unit cell is 1 because there are 8 atoms in the corner and one atom contributes to 8 other unit cells. So 8 into 1 by 8, 8 into 1 by 8 is equal to 1 atom. As there is a bulk atom in the center of the unit cell, it contributes to the total number of atoms in the unit cell. Now, A is the edge length of the unit. To summarize up, the definition of packing fraction is amount of space occupied by the sphere in the unit cell. And 3 types of unit cell we discussed are simple cubic, BCC and FCC. The total contributing atoms in simple cubic is 1 and its packing efficiency is 52.4%. And in case of BCC, the contributing atoms are 2 and the packing fraction or efficiency is 68%. In case of face center or FCC, the contributing atoms are 4 and the efficiency is 74%. To conclude, FCC has the maximum packing fraction and simple cubic as the least packing fraction. Thank you.
Hello friends, this is Sapan Joshi and I am gonna explain you about line defects. So it is a line along which a row of atoms are arranged anomalously. It has 3 types: edge, screwed and mixed. In edge, what happens is that a plane of atoms is terminated from the middle of crystal lattice and this causes distortion and misalignment. In edged ones, a helical path is traced around the linear defect and this causes distortion. The magnitude of distortion can be expressed in terms of Burger's vector. In some crystal lattices, the edged ones and the screwed ones both happens together and this defect is called as mixed linear defect. Thank you guys.
Now let me explain about bulk defects. Bulk defects, as the name suggests, are the defect in 3 dimensions. These include grain boundary, foreign inclusions or otherwise impurities, and cracks, which are also termed as voids. This defect normally arises during processing and the fabrication steps. When cluster of atoms are missing in a crystal, then there occurs a large vacancy or a void space. So the voids may arise in crystal when there is only a small electrostatic dissimilarity between the stacking sequences of closed packed planes in metals. So bulk defects also arises due to the addition of foreign particles or impurities. But in some cases, addition of foreign particles are added purposefully to strengthen the parent material. This procedure is called dispersion hardening, where foreign particles act as obstacles to the movement of dislocations.
Schottky defect. This is due to the missing of cation and anion from their position. A vacancy of one of the anion is accompanied by the vacancy of oppositely charged ion, so the electrical neutrality is maintained. Thus, overall density of substance decreases. The Schottky defect is found in AgBr, KCl, NaCl, ClS. This defect are possible in the ionic solids in which the cation and anion doesn't differ in size. An example of NaCl is given.
Hello everyone, I am Sudeep and I am going to explain the Virgo vector. The Virgo vector is a vector that represents the magnitude and direction of the lattice distortion of dislocation in a crystal lattice. The Virgo vector can be added just like the vector summation we do. The direction of dislocation should be same when Virgo vectors are added. Now the question is how to find the direction of dislocation. The Virgo vector of dislocation depends on which direction we go along the dislocation line. If all the directions goes upward, then V3 will be equal to V1 plus V2. If on the other hand, we let all line directions go outward from a node, then we will have V1 plus V2 plus V3 equal to 0, just like in nodal analysis. Without Virgo vector, we cannot say how much and to what direction a part of a plane is relatively displaced from the other part, which is distributed by a line boundary, as we call the dislocation. It is important to know how we define the size and direction of a Virgo vector and what we can say about the dislocation with the given Virgo vector. First of all, let's think about how the Virgo vector can be defined when there is a closed dislocation. The procedure is explained in the following stage, just follow them. First, decide the line direction at will, make a Virgo circuit around the loop according to the right hand rule, just cut the Virgo circuit along the shifted surface. So these are the steps you need to follow. So thank you, I hope you understand it well.